Moving on to our final characteristic of the NMR, we've talked about our number of signals, how many signals do we actually see, how many different non-equivalent hydrogens do we have in a molecule. We've talked about the chemical shift, where does it show up on the x-axis? We've also talked about integration, the area under the curve, or how many protons are represented in that signal. Now we want to be able to talk about multiplicity. This idea of splitting pattern is able to tell us an immense amount of information around the environment next door to our protons. So multiplicity is referring to the number of peaks that a signal is split into. So we could have a singlet when we just have one peak. A doublet is when we see a signal split with two peaks. A triplet is 3 peaks. A quartet is 4 peaks. Notice the symmetry as well with these peaks and how they look. A quintet would be 5. A sextet, 6. And a septet, 7. That's as far as we're going to go up. You can also call something a multiplet if it gets past, probably 5. A multiplet just means there's a bunch of stuff going on, a bunch of peaks. But notice how all of these, I just kind of want to look at this symmetry here where it goes up and down, and the middle peaks are always the tallest, right, on any one of these. And even with the doublet, they're even, right? The triplet, these sides are even, this is the tallest. I like to just represent that because that is true form of what we see for pure samples. If you don't see that, think something else could possibly be happening. Multiplicity arises from the actual magnetic effects that protons have on each other when they're neighboring. So we have these 2 carbons and we have HA and HB here, HA in red, HB in blue. Since the protons align with or against the external magnetic field, there could be 2 different types of relationships where HB is against the field or HB is with the field and HA is with the field or HB is without, things like that. There's options, right? And so with HA, what happens is HB will affect its peak. So multiplicity results from neighboring protons acting on each other. All right. Consider this example now where HA has 2 neighbors, 2 HB neighbors. So there's more options. Look at all these options. There's technically 3 possible environments, and these are the options. Think about coin tosses, right? And you don't need to know these environments, but what's important to be able to notice is that as we increase the number of neighbors, HA now has 3 neighbors. There are 4 possible environments. This is what we call the N+1 rule. When HA had 1 neighbor, it was split into 2 peaks. When HA had 2 neighbors, it was split into 3 peaks. When HA here in this example has 3 neighbors, it's split into 4 peaks. The N+1 rule says N is the number of neighbors, N+1 is the number of peaks that you see. So if HA has 3 neighbors, 3 plus 1, HA's signal will be split into a quartet, 4 peaks. And that's what we are going to see with all of our protons and multiplicity. When does this splitting actually occur? It's not every single proton. Equivalent protons do not split each other. So if you have a CH2 group and those 2 protons are on the same carbon and they are identical, or if you had 2 CH2 groups that were in a symmetrical molecule and you called them equivalent, that they would appear at the same position and be in the same signal, they resonate with each other. So they are equivalent and will not split each other. They don't count. To split each other, protons must be within 2 or 3 bonds. Non-equivalent geminal positions, if these were diastereotopic protons, they could split each other, or vicinal, right next door to each other. Next door neighbors, not down the block, all right? The neighbors that annoy you most are the ones that either live with you that are different or right next door to you, all right? If they are a couple houses down, they don't bug you. They don't interact with you that often, all right? So they have to be geminal or vicinal. There should not be another carbon in between those protons. These are just when we want to be able to look at which protons could possibly split. So the N+1 rule only applies to protons that are all equivalent, all right? So splitting patterns are observed for the protons that are shown below and can be more complex. So things like this proton right here has a proton here and it has a proton here. These two protons that I've drawn in that bluey green color are not chemically equivalent. We will not be discussing these protons and how they affect the red proton there because it's way too complex. We're just not going to deal with it. What we will deal with is a chemically equivalent neighbors. So here's a CH2 group, a methylene group. We have where it shows up on the integration or shows up on the chemical shift and it has an integration. We have 3 protons, 3 H's, and we have its signal right there as well. Now, what does this actually do? When we're looking at these two groups, they are adjacent to each other. So this isolated ethyl group, CH2, CH3, what happens? The two neighbors, I'll call these A, and I'll call these B. The A signal has N+1 or 3+1 neighbors, which is 4 peaks. That's why we see 1, 2, 3, 4. For B over here, the 3 hydrogens, N+1, 2 neighbors, the blue guys. So that would be 3 peaks. 1, 2, 3. Beautiful. Now, what's really important to note here, simple splitting, notice the distance between these peaks is the same as the distance between the other set of peaks. This splitting pattern, not only do the peaks match up to the N+1 rule for being the correct number of neighbors, but the distance between those split peaks is also the same. This set distance is not the same as this distance. So these two signals are not neighboring each other. Very, very important. Their actual coupling constant, which is the J value, it goes in depth with the J value in the textbook. I'm not going to be talking about those values, but what's really important is this distance here is going to be consistent for neighbors. All right, so because these two distances are different, these are not neighbors. They might be on the same molecule, but they're not splitting each other. These guys, let's just zoom in here a little bit. This distance is the same as this distance. So these must be neighbors. Because not only does the N+1 values match up, but the coupling constants, the distance that that signal is split is consistent. All right, some things that I just want to present that are really good to remember, really good to observe. And these are things that we'll see a lot of. If you see a singlet with 9 H's, all right, 9, that suggests the presence of a tert butyl group. Remember, right here, there is no hydrogen. So no neighbor there, meaning N+1, 0 + 1 is 1. That's the only time we get a singlet, when there's an adjacent carbon that has no neighbor. 3 CH3 groups add up to 9 protons, and those are chemically equivalent, all right? An isolated isopropyl group, right, has a carbon with 2 methyl groups and a single hydrogen. That hydrogen, 6 plus 1 neighbors, should have 7 peaks. 1, 2, 3, 4, 5, 6, 7. The 6 methyl hydrogens, right? The 2 CH3 groups add up to 6. One neighbor should be split into 2 peaks. Beautiful. Nice. Let's observe some splitting for ethanol. All right. So again, let's label how many hydrogens we expect. I'm going to make this a little bit bigger. Put in our hydrogens. We should expect to see 3 sets of signals. 1, 2, 3. Now, the OH proton, that's what I want to talk about first. 1 hydrogen there, right? We would expect it to show up somewhere between 2 and 5 ppm, typical for an OH proton. We'd expect the integration to be 1 hydrogen. And what happens with a proton bonded to a heteroatom, stuff like nitrogens, oxygens, sulfurs, is that they do not contribute to splitting and they do not get split. Think about that oxygen as a huge hedge that a neighbor has that does not want you to be seen or does not want to interact with you. Notice this 1 hydrogen peak right here, integration of 1 singlet appearing around 2.2. That is the OH peak. 2 hydrogens here, we would expect to see 2 H's, right? We know they're adjacent to an oxygen. So again, a methylene group, 1.2 ppm typically for the base. Add 2.5, we predict 3.7 ppm based off of our calculations, and that's what we see, 3.7. Nice. Now, it has, we're gonna make it the right color, 1, 2, 3 neighbors. So 3 plus 1, I would expect a quartet. And that's what I see. Beautiful. Now, the methyl group starts at 0.9. It's beta to an oxygen. So it's 1/5 of 1 or 0.2 being added onto its shift. So that's a 1.1 ppm. Excellent. 1.2, that's fine. Close enough, right? Very, very close. Now here we have the 2 neighbors that we saw from the CH2 group. 1, 2 neighbor. So 2 plus 1 equals a triplet. Excellent. Now we can dissect not only how many sets of hydrogens do we see, how many signals, we know where they appear, their chemical shift, we know their integration values and assess how many protons are represented there from the computer data. We also can predict the splitting pattern. Now, the hydroxyl protein does not go into splitting. I said it acts as like a hedge. The reason for not undergoing the splitting is because of the rapid exchange of protons with trace amount of acid that could be in the solution, right? So because of that, those protons are switching back and forth. So the exchange of proton transfers that could be happening in the solution, happening in the NMR, blurs the shielding and de-shielding effects of neighboring protons. So sometimes we don't see that splitting occur. Using NMR for a aromatic compound, these 3 molecules might be difficult to distinguish by IR or mass spec. That should be an or mass spec, sorry. But what's great about NMR is that they are more easily distinguished because of the equivalent sets of protons, right? These 3 these two and these two, we would see 3 signals for this first guy when the methyls are right next to each other. If the methyls are 1, 2, 3 in their relationship, we see 4 signals. And if they're 1, 2, 3, 4 exactly opposite, we see 2 signals. All right, so there are ways to be able to determine more structurally sound things when looking at proton NMR. Best thing to be able to do here for wrapping up our proton NMR idea is when given a molecular formula and a proton NMR spectrum, which is what you typically will be given, 5-step process. Calculate the degrees of unsaturation like we've been doing from the beginning. Consider the number of signals and integration based off of what you see in this, the spectrum. Start analyzing things, start writing things down, right? Analyze each signal, draw fragments. Now, it doesn't mean that the molecule's splitting apart. It's not mass spec fragments. We're talking about if I see a carboxylic acid, if I see aromatic protons, start writing down different pieces of the puzzle. Then we can start completing and the structure by putting these pieces of the puzzle together based off of the neighboring multiplicity that we see. So it's really degrees of unsaturation followed by the number of signals and the integration and the chemical shift. Last thing that we want to do is identify multiplicity so that we can piece it all together. All right, we'll practice a lot more in class. I think the best way for this to be really understood is by practicing. The last few sections that we got going on here, talking about the carbon-13 NMR. This is helpful still. I know there's a lot into proton NMR that we use, and it's really, really helpful to determine structure. And I know at this point, probably a bunch of you are like, well, I just like the proton NMR. Let's just stop here. Carbon-13 NMR is still really, really helpful. We talked about this before with having an odd number in the nucleus, right? Proton 1, that idea is usually because that is the most abundant isotope of hydrogen, and we tend to have a lot of hydrogens in our organic compounds. These signals are really easy to obtain. They're really strong. Carbon-13 only accounts for 1% of the carbons in nature, 1.1%. So you really need a sensitive NMR and a really concentrated sample to do a proton or to do a carbon-13 NMR. For proton NMR, we talked about where the chemical shift was, the splitting patterns, integration, all of those are important. The only thing that's important in carbon-13 NMR is the number of signals and the chemical shift. So there's 2 characteristics, signals and shift, that we will be considering. In the carbon-13 NMR, we do have splitting with protons and carbon-13, and it's often so complex that we can't read it. So what we have is a decoupled carbon-13 NMR signal. What we do is we try to decouple the number of signals so that it's easier to determine the carbon-13 spectra. And so what we'll see is that all of our carbon-13 spectra will be singlets. All right, so we won't see any doublets or triplets or anything like that, because what happens in carbon-13 NMRs, if we don't decouple, is that the protons actually get involved, and that's just not fun. So we can compare proton NMR to carbon-13 NMR in the same idea as different frequencies of energy to excite and resonate nuclei. We will see a TMS standard, but carbon-13 NMR generally appears between 0 ppm and 220 ppm. So there's a bigger range here because of the carbon nuclei having 13 species, 13 protons and neutrons in the nuclei rather than hydrogen's just 1. So carbon-13 NMR is a unique type of signal. And so each carbon-13 NMR spectrum represents a unique type of carbon. Planes and axes of symmetry can cause carbon atoms to be electronically equivalent. So let's take a look at a couple of molecules and we'll start to see how symmetry affects, right? Just the same as proton NMR. Just the same as proton NMR, we see how symmetry can affect our molecule. So this is our same idea as what we were talking about at the end of the proton NMR. 3 different types of benzene with 2 methyl groups being distributed across. When we see a plane of symmetry, boop, 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 right down there, this side, I'll label this A, is the same as that side. B, same as that side. C, and D, right? Same plane of symmetry, just locating a couple different places. We have 1 carbon here. We have 2 carbons over here that are the same. These are the same. These are the same. That's different, right? And when we have perfect symmetry, whoo, we have a lot of things that are the same. The methyl groups, B, B, and then all 4 of these leftover carbons are the same. So when we're thinking about structure, what's really important is to be able to find symmetry or lack thereof, right? Symmetry right here. So we can expect A, B, and C, 3 signals for something like pentane, right? Awesome. If we were to throw in something that's not symmetrical, now our molecule is not symmetrical anymore, all 5 of these carbons are different, right? Beautiful. So same way that we've dissected the molecules before in talking about symmetry and looking at equivalent carbons, now it's a little bit easier, I think, in carbon-13 NMR than in proton NMR because you don't have C2 groups, right? You have just plain old carbons, and we're not focusing on multiply attached hydrogens. Like the proton signals, chemical shifts for carbon-13 NMR are affected by shielding or de-shielding. Again, the same way, sp3 hybridized carbons are usually down here at the 50 to 0 ppm range. And then sp hybridized and sp3 hybridized with de-shielded, some electronegative atoms appear in the middle. So our triple bonds and carbons to nitrogens, carbons to oxygens. sp2 hybridized carbon atoms are in between 100 and 150 ppm. And then our carbonyl compounds are between 150 and 220. So let's just start recording some stuff here. This is what a typical spectrum will look like. This is an ester compound that I'm looking at here, and there are 5 carbons up at the top in that structure. What we want to do here is just be able to match to start off the bat. We'll get into harder questions when we meet, but matching the carbons here, they are labeled. So I just want to make sure we know which ones are which. Again, CdCl3 is a type of solvent. It's a deuterated chloroform so that there are no protons in it, so that it is just a solvent for us, all right? Now, the C2, what's labeled as C2 way down here, is most likely our carbonyl. Why? Because it is an sp2 hybridized carbon and it appears greater than 150. Remember, between 150 and 220 are our carbonyl compounds. So that's C2. Coming up here, this range, if we want to look at which carbon is C3 up here. Remember, shielding and de-shielding, just like in proton NMR. We don't have to do any math here, but we do know the further downfield, the further to the left, the closer you are to an electronegative atom. So the carbon, the CH2 group attached to the oxygen of the ester is closest to the most electronegative atom, oxygen. And so that is why we're going to label that CH2 group as number 3. So I'm just going to label closer to oxygen of ester for our reason why. All right, let's look at C1 here, the next carbon in our chain. Which one of our leftover outer terminal carbons is C1? Most likely it's going to be this one because it's alpha to the carbonyl, right? And then our final carbon 4 here. Beta, 2 oxygen. So again, doesn't get shifted downfield as much. And it is the furthest away from any sort of electronegative source. So this is how we can whittle through a carbon-13 spectrum. Now, the distortionless enhancement by polarization transfer, or DEPT, carbon-13 NMR spectroscopy is extremely helpful because carbon-13 doesn't give, only gives singlets, and it doesn't provide information about numbers of hydrogens attached to each atom or neighbors or anything like that. Carbon-13 by itself is actually pretty difficult to start to analyze. We like using DEPT carbon-13 NMRs because they can actually provide more information to the number of hydrogen atoms attached to each carbon. Like this, DEPT 90 only shows CH signals. What? That's pretty cool. DEPT 135 will show the CH3 and CH and give them a positive signal that shoots upward, just like our typical signals. I'll show you what that looks like in a second. The CH2, it will actually shoot that into the negative in the downward position. So now what DEPT 90 and 135 can do is actually elucidate the type of carbons we have, CH, CH2, or CH3, and be able to look at the signals that stay or the signals that disappear as being able to elucidate that information. Let's go ahead and just look at this chart. This chart is very, very helpful. Broadband decoupled is when everything shows up and everything's a singlet spike. That's what we just did, right? DEPT 90 only shows a CH group. Nice. So you can take a broadband decoupled and a DEPT 90 and compare them and say, oh, any peak that shows up on my DEPT 90 and was on my broadband decoupled carbon NMR, that must be a CH group. Any group that disappeared is not a CH group. If it doesn't show up on DEPT 90, it's not a CH group. And then a DEPT 135 will be able to elucidate that CH2 group. It also important, remember we've talked about this since IR, not showing signals is just as important as showing the signals. So look to where there's absences on these, right? A DEPT 135 will invert the CH2 group signal and make it go downward, and it will eliminate our carbon groups with just tetrasubstituted carbons. So this could be carbonyl groups. This could be the carbon that's holding 3 methyls in a butyl group, things like that. So we want to compare, right? We wouldn't ever do a DEPT 135 without doing a broadband decoupled, or a DEPT 90 without doing a broadband decoupled carbon NMR spectrum. So we have diethyl phthalate up here. I chose this one just because it was of the symmetry, honestly, and it's real life application with the phthalates. Diethyl phthalate here, let's just identify a couple of signals, right? A, B, C, D, E, F on the top is the same as that on the bottom. And so we should see 6 peaks. But what's really, really important here is the idea of a couple of these that we see. The aromatic CHs are kind of shoved in here, and aromatic C for carbon D is a little hard to see as well. But we'll try to elucidate these 6 peaks as much as possible, okay? And so we do see 1, 2, 3, 4, 5, 6 peaks. I'm not going to label them A, B, and C yet because I want to make sure that we see that there are 6 peaks. We understand what those 6 peaks could represent, and now we're going to try to elucidate with the decoupled carbon NMR, the DEPT 90, and the DEPT 135, what each one of these is. So again, looking and referring to our table that we just saw way up here, table 15.4, what we want to be able to do is identify which groups are carbons, which ones are CHs, which ones are CH2s, and which ones are CH3s. So without looking at the structure right now, let's just start to identify what we see in comparison from the decoupled carbon-13 NMR to the DEPT 90. Remember, DEPT 90 only shows CH groups. This signal and this signal still appear. I'm going to highlight them. This one and this one, these two. The signal 3 and 4 still appear. So these must be CHs. They also appear in the range around 120, 130. So they must be aromatic CHs, right? Those sp2 carbons with 1 hydrogen, all right? Now, let's move up to the depth 135. There is still our 2 CH groups, right? We see this negative peak for this one right here. So this must be a CH2 group, right? Because the CH2 group in a depth 135 is inverted. Beautiful. And then the last peak that I want to see here was absent in the depth 90, but present in the depth 135. That means it must be a CH3 group, all right? Awesome. Things that are absent in both the depth 135 and the depth 90 are going to be our plain old carbons, carbons without hydrogens. We have a few of them. This guy up at 165, and this one, which was around 135. Now, we have 2 carbons in that structure, D and C, that are those C groups without hydrogens. We're going to label this as carbon C and this one as D. Why? Because we know the carbonyl would be, the carbonyl carbon is going to be more de-shielded because it's double bonded to an oxygen, and so it should be further downfield, right? Just like we expected. The 2 aromatic groups, E and F, E is probably the one that's closest to the carbonyl. F is probably the one that is furthest upfield, further away from the carbonyl, right? So we would probably label E as the signal number 4 there, and F as signal number 3. CH2 group, B, the carbon adjacent to the oxygen of the ester. And then finally, A, the CH3 group. Excellent. So this identification of CH, CH2, and CH3 groups with the depth 135 and the depth 90 with the CH groups is extremely helpful to start to elucidate the positions of each of these carbon peaks. Also, don't forget those peaks highlighted in green. What is absent from both the depth 135 and the depth 90 are our carbonyl groups and our fully substituted carbons, the carbons with no hydrogens. Where can we see NMR before? In real life, if you've ever seen or had an MRI done, magnetic resonance imaging, it is essentially a proton NMR, just taken on a human body, right? The body is analyzed rather than a sample in an NMR tube, but we are made up of a bunch of different nuclei, and different tissues actually have different concentrations of protons. So the MRI gives a 3D image of different types of tissue. Radio waves and magnetic fields are very, very mild, so that we have no side effects. But again, you're sitting in a pretty big NMR when you think about getting an MRI in the medical field. So this is a truly medically applied type of instrumentation, which is just really awesome that we can do this with the human body.